There are three methods to charge a body, namely charging by friction, conduction, and induction. Let us first look at charging a body by friction. When two uncharged or neutral objects made of different materials, say a glass rod and a silk cloth, are rubbed against each other, both objects get electrified due to a transfer of charges. This process is called charging by friction. When rubbed, the glass rod loses a few electrons to the silk cloth. This deficit of electrons on the glass rod makes it positively charged, and the excess of electrons makes the silk cloth negatively charged. In this method, there is a transfer of electrons from one body to another. The material that gains electrons is negatively charged, and the one that loses electrons is positively charged. In this case, silk is negatively charged and glass rod is positively charged. Let us now look at how a body can be charged by conduction. If we momentarily touch the positively charged glass rod to an uncharged pith ball, the pith ball becomes positively charged too. This process of charging by bringing a charged body in contact with a neutral body is called charging by conduction. In this case, some electrons are transferred from the pith ball to the glass, and thus the glass becomes less positively charged by gaining the electrons. We observe that both bodies involved in this method of charging by conduction acquire the same type of charge once the process is complete. Let us illustrate this by a numerical example. Let us assume that initially glass has a deficit, Ng, of 200 electrons. Using the quantization of charge principle, that is, Q is equal to Ne, we see that the charge on the glass is Qg equal to plus 200E. Now, when this glass rod was in momentary contact with the pith ball, let us assume that because of the electrostatic attraction, a few electrons, say Npg equal to 50, are transferred from the pith ball to the glass rod. Now, the pith ball has the deficit Np of 50 electrons, which implies that the charge on the pith ball, Qp, is equal to plus 50E. Similarly, the glass now has a charge of plus 200E minus 50E, where minus 50E is the charge due to the 50 electrons gained by the glass. Therefore, the effective charge on the glass is plus 150E. Hence, it has become less positively charged compared to its original state. We can also charge a body without contact, as in the first two methods. The third method to charge a body is induction. When a charged object, A, is placed near an uncharged object, B, object A induces an unlike charge on the near side of B and a like charge on its far side. In this case, the charges inside B are only polarized and no transfer of charges takes place. This process of polarization of the charge on an uncharged body, when a charged body is held close to it, is called induction of charge. For example, bringing a negatively charged rod near a neutral metal sphere will induce a positive charge on the near surface of the metal sphere and a negative charge on the far side. When the negatively charged rod is brought near the metal sphere, a few free electrons in the metal sphere move away to the far side of the metal sphere due to repulsion, leaving a positive charge on the near side. This charge is temporary. That is, if we move the glass rod away, the sphere returns to its original uncharged state. When the negatively charged rod is held close to the metal sphere, the charges in it are polarized due to induction. Now, if we earth the far side of the metal sphere using a conducting wire, the electrons on the far side of the metal sphere flow into the earth. However, the positive charges on the near side of the metal sphere are held at rest by the negatively charged rod. Now, if we take away the glass rod from the sphere, the positive charge on the metal sphere distributes uniformly across the sphere. In this way, we can retain the charge on the metal sphere. In the method of charging by induction, we observe that the induced charge is always equal to the inducing charge for a conductor. Now, we keep two metal spheres, A and B, supported on insulated stands, in contact with each other. When we bring a positively charged glass rod near sphere A, negative charges accumulate on its near side, and positive charges accumulate on the far side of sphere B, according to the principles of attraction and repulsion respectively. Now, separate the spheres by a very small distance, keeping the charged glass rod near them. There will be a force of attraction between A and B. Then, if we move away the glass rod, sphere A will retain the negative charge, and sphere B will retain the positive charge. We observe that the excess charge on the metal spheres distributes uniformly later. Coulomb's law, stated by Charles Coulomb, a French physicist, to find the electrostatic force of attraction and repulsion between two charged particles. This law was defined after an extensive study of force between the charges using a torsion balance. A torsion balance has an insulating rod with a metal-coated ball at one end and a balancing sphere at the other. This rod is suspended with the help of a suspension fiber. The graded circular scale gives a measure of the displacement of the sphere due to repulsion. Another static sphere, which is identical in size to the metal-coated ball, is placed at the zero mark. A micrometer screw at the top helps adjust the distance between the free and rotating spheres. The static sphere is first given a charge Q by bringing a charged object in contact with it. Then, the rotating sphere is brought in contact with the static sphere using the micrometer screw. Due to conduction, the charged static sphere now loses half of its charge, that is, Q by 2 to the other sphere. This happens because the two metal spheres are identical in size. Now, both the spheres are identically charged, with a charge of q/2 each. They start repelling each other since like charges repel. The measure of repulsion is the amount of deflection or the angle through which the sphere attached to the rod is displaced. The static sphere is now discharged by grounding. To recharge the static sphere, the rotating sphere is brought in contact with the static sphere using the micrometer screw. Again, due to conduction, the spheres now have a charge q/4 each. As both the spheres are identically charged, they repel each other. However, the angle of deflection observed is lesser than the previous observation for charge q/2 on each sphere. Therefore, it can be concluded that as the charge on the spheres decreases, the force of repulsion between them also decreases. From these experiments with charged spheres at constant distances, it was concluded that the electrostatic force between two charges is directly proportional to the product of the charges. If the charges are q1 and q2, then electrostatic force F between them is proportional to q1 into q2. Let this be equation 1. Now, keeping the charge on each sphere constant, if the distance between the charged spheres is varied using the micrometer screw, the angle of deflection is found to be inversely proportional to the square of the distance r between the charges. Since the force of repulsion is proportional to the angle of deflection, we can say that the electrostatic force F between the charges q1 and q2 is inversely proportional to the square of the distance r between the charges. Let this be equation 2. Thus, according to Coulomb's law, the electrostatic force between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. Hence, the electrostatic force F between charges q1 and q2 separated by a distance r is proportional to q1 q2 by r square. Let this be equation 3. A constant of proportionality k is used to get the equation F is equal to k q1 q2 by r square. Let this be equation 4. If the charges are separated in free space, that is, air or vacuum, the value of the constant k is equal to 1 by 4 pi epsilon naught, where epsilon naught is called permittivity of free space. Thus, the electrostatic force F is equal to 1 by 4 pi epsilon naught q1 q2 by r square. In SI units, the value of the proportionality constant K is approximately equal to 9 into 10 power 9 Newton meter square per Coulomb square, and the value of epsilon naught is equal to 8.85 into 10 power minus 12 Coulomb square per Newton meter square. Hence, F is equal to 9 into 10 power 9 into Q1 Q2 by R square. Using Coulomb's law, a unit charge can be defined as one that experiences an electrostatic force of 9 into 10 power 9 Newton when placed at a distance of 1 meter from another unit charge in free space. Let us now study Coulomb's law in vector form. Let the charges Q1 and Q2 be at positions specified by the position vectors R1 and R2 with respect to the origin O. The vector R21 is equal to R2 minus R1 joins Q1 and Q2. The force on Q1 due to Q2 is F12. The force on Q2 due to Q1 is F21. In vector form, we can express Coulomb's law as shown. If Q1 and Q2 are like charges, they repel. In this case, the product of the charges Q1 and Q2 will be positive. The unit vector R12 cap is given by equation 5. Here, the force F12 will be in the direction of the unit vector R12 cap. If Q1 and Q2 are unlike with respect to each other, the force F12 will be in the direction of the unit vector R21 cap as given in equation 6. Since unlike charges attract each other. In this case, the product of the charges Q1 and Q2 will be negative. The unit vector R21 cap is given by equation 7. According to Newton's third law, Q2 experiences an equal and opposite electrostatic force to the one experienced by Q1. Therefore, we can write F21 is equal to minus F12. Let us now consider a system of charges Q1, Q2, Q3 and so on till Qn as shown in the figure with position vectors R1, R2, R3 till Rn with respect to the origin O. We know that electrostatic force, as given by Coulomb's law, exists between every pair of charges of the combination. To find the net force on any charge in such a system, we first calculate the electrostatic force on that charge by each and every other charge of the system. Then, the net electrostatic force on that charge is equal to the vector sum of the individual electrostatic forces on that charge due to every other charge of the system of charges. The individual forces are unaffected by the presence of other charges in the configuration. This principle is called the principle of superposition. For example, if the charge Q1 is considered, then, according to principle of superposition, the net electrostatic force on the charge Q1 is F1 equal to F12 plus F13 plus so on till F1n. Let this be equation 8. F12 is the force on the charge Q1 due to Q2 and is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 square into R12 cap. R12 is the distance between Q1 and Q2, and R12 cap is the unit vector in the direction of the force F12. F13 is the force on the charge Q1 due to Q3 and is equal to 1 by 4 pi epsilon naught into Q1 Q3 by R13 square into R13 cap. R13 is the distance between Q1 and Q3, and R13 cap is the unit vector in the direction of the force F13. Proceeding in this manner, we obtain F1n is the force on the charge Q1 due to Qn and is equal to 1 by 4 pi epsilon naught Q1 Qn by R1n square into R1n cap. R1n is the distance between Q1 and Qn, and R1n cap is the unit vector in the direction of the force F1n. Now, using F12, F13, F1n in the principle of superposition, we have F1 as in equation 9. Thus, net electrostatic force on Q1 is F1 is equal to 1 by 4 pi epsilon naught into Q1 into sigma I equal to 2 to nqi by R1i square into R1i cap. Let this be equation 10. To understand the superposition principle more clearly, consider the charge configuration consisting of charges Q1, Q2, and Q3 with position vectors R1, R2, and R3 respectively with respect to the origin O. F12 is the force on the charge Q1 due to Q2 and is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12 square into R12 cap. R12 is the distance between Q1 and Q2, and R12 cap is the unit vector in the direction of the force F12. F13 is the force on the charge Q1 due to Q3 and is equal to 1 by 4 pi epsilon naught into Q1 Q3 by R13 square into R13 cap. R13 is the distance between Q1 and Q3, and R13 cap is the unit vector in the direction of the force F13. To find the net force F1 on Q1 due to the other charges in the system, we should apply the principle of superposition. That is, we should have F1 is equal to F12 plus F13 vectorially. This we can do by using parallelogram law of vectors as shown. Then the direction of F1 will be along the direction of the diagonal of that parallelogram. The magnitude of F1 will be equal to root over F12 square plus F13 square plus 2F12 F13 cos theta, where theta is the angle between F12 and F13. By knowing the values of the parameters involved, the net force F1 on Q1 can be calculated. Now, let us consider the electrostatic force between two electrons having a charge equal to basic unit of charge E, which is equal to minus 1.6 into 10 power minus 19 coulomb, and separated by 1 meter in vacuum. The magnitude of the electrostatic force between them, according to Coulomb's law, is given as Fe equal to 1 by 4 pi epsilon naught E square by R square, where R is equal to 1 meter. Substituting the values of the various parameters, we have the electrostatic force between the two electrons is equal to 23.04 into 10 power minus 29 Newton. Let this be equation 11. Let us now compare the electrostatic force between these electrons with the gravitational force between them. The gravitational force F between the electrons is G into M1 M2 by R square, where M1 and N2 are the masses of the electrons, which are equal to 9.1 into 10 power minus 31 kilogram each. Substituting the values of the various parameters, we have the gravitational force between them is equal to 552.34 into 10 power minus 73 Newton. Let this be equation 12. Dividing equation 11 by equation 12, we have the ratio between electrostatic and gravitational forces, and we can see that the electrostatic force is enormously greater than the gravitational force. Consider a charged particle with a charge Q held at rest at the origin of an imaginary coordinate system. If we place a charge Q0 at a point P near charge Q and release it, then the charge Q0 accelerates away from the origin. This acceleration is due to a force on charge Q0. Now, let us remove charge Q from the origin and reintroduce charge Q0 at the same point P. Charge Q0 does not accelerate now and remains at rest. This means that the force experienced by Q0 is due to charge Q. We say that since charge Q0 is in the electric field of charge Q, it experienced a force. An electric field is a region in which the influence of a charge is felt. Since charge Q produces this electric field, this charge is called the source charge. Charge Q0 is called a test charge, as it is used to study the effect of the electrical field created by charge Q. We can use Coulomb's law to calculate the force on Q0 due to Q. The electrostatic force on Q0 due to charge Q is F is equal to 1 by 4 pi epsilon naught Q, Q0 by R square into R cap, where R cap is the unit vector along the direction of OP. Let this be equation 1. Now, if Q0 is a unit positive charge, that is, Q0 is equal to plus 1 Coulomb, then the electrostatic force as denoted by equation 1 becomes 1 by 4 pi epsilon naught Q by R square into R cap. Let this be equation 2. Equation 2 indicates the electric field strength or intensity of electric field E, which is the force on a unit positive charge acting at a particular point in the electric field. Therefore, the electric field strength due to charge Q at point P is E equal to 1 by 4 pi epsilon naught Q by R square into R cap. Let this be equation 3. Electric field strength E is a vector quantity pointing in the direction of the force on a unit positive charge at a point in the electric field. In SI, it is measured in Newton per Coulomb or volt per meter. From equations 1 and 3, the force on the charge Q0 can now be expressed as F is equal to Q0 E. Let this be equation 4. Hence, we can write the electric field strength at P as E is equal to F by Q0. Let this be equation 5. The above equation is valid as long as the test charge Q0 is very small and its own electric field is negligible. Hence, at point P, we write the electric field strength E as F by Q0 limit Q0 tending to 0. For a given distance R from the source charge Q, the value of 1 by 4 pi epsilon naught is always constant, and hence E, as given by equation 3, will also be constant. Hence, the electric field strength E at any distance R from the source charge Q is independent of the test charge Q0. It varies with R cap and is inversely proportional to R square. The electric field at any point in the electric field is finite and is 0 only when distance R is equal to infinity. In the electric field of a positively charged particle, the electric field strength vector E at any point in the field always points away from the charged particle in a radially outward direction. The point charge Q0 will be accelerated in the direction of the electric field as it experiences an acceleration A due to the force due to the electric field, and the acceleration is expressed as A is equal to Q0 E by m, where m is the mass of the particle. In the field of a negatively charged particle, The electric field strength vector at any point in the field always points towards the charged particle in a radially inward direction. Here, the point charge Q0 in this electric field will be accelerated in the direction opposite to the electric field. The magnitude of acceleration of Q0 is the same regardless of whether the electric field is due to source charge plus Q or minus Q. For a charge Q, at all points on an imaginary sphere of radius r around it, the electric field strength will be equal in magnitude and will be equal to 1 by 4 pi epsilon naught Q by r square. There is a spherical symmetry with respect to the magnitude of the electric field strength E in the electric field of charge Q. Consider a region consisting of point charges Q1, Q2, Q3, Q4, and so on in air, or a vacuum with position vectors R1, R2, R3, and so on relative to the origin O. Let P be a point in this region. The net electric field strength E at point P is the superposition of all the electric field strengths E1, E2, E3, E4, and so on due to the individual charges. The net electric field strength E at point P will be equal to the vector sum of all the electric field strengths E1, E2, E3, E4, and so on. Then, E is equal to 1 by 4 pi epsilon naught into Q1 by R1 P square into R1 P cap plus Q2 by R2 P square into R2 P cap plus Q3 by R3 P square into R3 P cap, and so on. Here, R1P is the distance from Q1 to P, and R1P cap is the unit vector in the direction of Q1 to P. R2P is the distance from Q2 to P, and R2P cap is the unit vector in the direction of Q2 to P, and so on. The net electric field strength E can now be written as 1 by 4 pi epsilon naught sigma I1 to n Qi by RIP square into RIP cap, where RIP cap is the unit vector in the direction of the net electric field strength E. Consider a situation where charge Q is accelerating. Then, it produces electromagnetic waves, which propagate at the speed of light. Here, Q0 is also accelerating in the electric field of Q, and there will be a force on Q0 due to the electric field of Q. This force on Q0 due to Q is actually caused by the electromagnetic waves generated by the accelerating charge Q, and which travel from Q to Q0 at the speed of light. Thus, an accelerating charged particle is a source of electromagnetic waves. For example, electric current applied to a solenoid creates an electromagnetic field around it.